Hey everyone, and welcome to our interactive digital classroom. I am absolutely thrilled to guide you through today's explainer on one of the most fundamental, fascinating, and frankly, everywhere all at once topics in chemistry. Today, we are conquering oxidation and reduction. Whether you're prepping for your upcoming exams, or you're just kind of curious about why the world around you changes color, rusts, and ages, well, you're in the exact right place. We're going to master these concepts together, step by step, like true chemistry pros.
All right, here's our roadmap for today's explainer. We'll start with the concept dependency map, move into redox reactions in action, explore the real-life effects of corrosion and rancidity, and wrap up with some really handy memory tricks in our conclusion.
So, let's jump right into Section 1, the concept dependency map, understanding the rules.
To truly get a handle on this topic, you need to grasp this core hierarchy. Oxidation and reduction are exact opposites. Think of them as playing a constant, microscopic tug-of-war. A substance is oxidized when it gains oxygen atoms, loses hydrogen atoms, or, and this is absolutely crucial, loses electrons. Conversely, reduction is the exact mirror image. A substance is reduced when it loses oxygen, gains hydrogen, or gains electrons. If you can just picture this constant back-and-forth exchange happening, you've already won half the battle here.
Now, you might be wondering about a common trap so many students fall into. They think oxidation is only about oxygen. I mean, the word oxygen is literally right there in the name, right? But the scientific reality is far more dynamic. Oxidation fundamentally means losing electrons. When a substance acts as an electron donor and loses those negatively charged electrons, it actually becomes more positively charged. That electron transfer, that is the true heart of the reaction.
Moving right along to Section 2, redox reactions in action, simultaneous chemistry. So, the really crucial point here is that oxidation and reduction are completely inseparable. You can't have one without the other. They are a redox pair that always happen together. Let's break down a classic reaction visually to see this in action. Here's the first half of the story, hydrogen gas reacting. Notice how hydrogen gains an oxygen atom to become H2O, water. Because it's gaining oxygen, this specific part of the process is for sure oxidation.
But wait a second, where did that oxygen come from? It didn't just magically appear out of thin air. And that brings us to the exact same moment in the reaction. Copper oxide, or CuO, is losing its oxygen atom to become pure copper metal. Because it's releasing that oxygen, it's undergoing reduction. Put them together, CuO plus H2 turning into Cu plus H2O, and you have this beautiful simultaneous redox reaction where one atom gives and the other takes.
And this perfectly illustrates how we write these out chemically. Take our first formula. Copper metal is heated with oxygen to form copper oxide. That's copper gaining oxygen, so it's oxidized. In our second example, zinc oxide reacts with carbon to form zinc and carbon monoxide. Here, carbon is oxidized to CO, while zinc oxide is reduced to pure zinc. And the last one is pretty spectacular. Sodium literally burns in oxygen. 4Na plus O2 yields 2Na2O. Sodium loses electrons and gains oxygen. It's chemistry in high gear. Okay, let's step out of the lab for a minute. Section 3, real-life effects, corrosion. Corrosion happens when metals meet their everyday environment, specifically moisture, acids, and oxygen, and they just begin to deteriorate. It causes massive structural damage globally. When shiny copper reacts with carbon dioxide, oxygen, and moisture in the air, it forms a green patina. That green layer is actually basic copper carbonate. Silver, on the other hand, reacts with hydrogen sulfide gas to form a black silver sulfide coating. We call that tarnishing. And of course, iron. Iron reacts with oxygen and water to form reddish-brown hydrated ferric oxide. Yep, what we all know and hate as rust. Because rust completely destroys structural integrity and is incredibly costly to repair, engineers have developed some strong defensive methods. The three main ones are pretty straightforward. First, painting, which simply creates a basic protective barrier. Second, greasing and oiling, which actively repels moisture and oxygen. And third, a highly industrial, super effective process called galvanization, which uses a specialized zinc coating. Let's actually walk through this hot dip galvanization process step by step, because it's fascinating. Step 1, the iron surface is rigorously cleaned to remove any dirt, oil, or existing oxide layers. Step 2, a chemical flux is applied, which helps the liquid zinc flow and bond tightly to the iron. Step 3, here's where the magic happens. The iron is dipped into a molten zinc bath sitting at a scorching 450 degrees Celsius.
At this intense temperature, a complex electron exchange happens, binding the metals together. Finally, step 4, the metal is cooled, leaving a perfectly finished, rock-solid protective zinc layer.
But you might be asking, why zinc? What makes galvanization so special compared to just painting it? Well, zinc provides double protection. First is barrier protection, where the zinc literally seals the iron away from the surrounding environment. But even if that barrier gets deeply scratched, it provides sacrificial protection. Because zinc is more reactive, it will gladly sacrifice its own electrons before the iron does. The zinc corrodes first, completely saving the iron structure underneath. It is literal chemical self-sacrifice.
Let's pivot to another everyday effect we've all experienced. Section 4. Real-life effects, rancidity.
Have you ever opened an old bag of chips, or maybe smelled old butter and noticed a terrible, stale, cardboard-like odor? That right there is rancidity. It is the chemical breakdown that occurs when fats and oils are exposed to oxygen in the air for an extended period. The oxygen relentlessly attacks the fat molecules, resulting in a really unpleasant taste and smell. It's oxidation ruining our snacks.
Thankfully, chemistry also gives us smart solutions to prevent our food from going bad. Food scientists do 3 main things. First, they add antioxidants, which are natural or synthetic compounds that hit the brakes on the oxidation process. Second, they use airtight containers to physically block out oxygen. And third, and this is honestly my personal favorite, inert gas flushing. When you buy a puffy bag of potato chips, that's not just air inside. The manufacturers have flushed out the oxygen and replaced it with nitrogen gas. Nitrogen is unreactive, meaning the oils on the chips won't oxidize and go rancid while sitting on the supermarket shelf. Pretty clever, right?
All right, we are in the home stretch. Section 5, Memory Tricks and Conclusion.
When it comes to your exams, the absolute easiest thing to mix up is which process loses electrons and which one gains them. So here is a classic memory trick you can use. Oil rig. Just picture a giant oil rig out in the ocean. OIL stands for oxidation is loss. RIG stands for reduction is gain. If you just remember oil rig, you will always know exactly how those tricky electrons are moving.
Now, if oil rig doesn't quite click for you, try this alternative mnemonic, Leo-Jur. Think of a lion roaring. Leo, lose electrons equals oxidation. Jur, gain electrons equals reduction. Keep these little tricks at your fingertips, and I promise you will be able to identify complex redox reactions effortlessly on test day.
Before we wrap up, I want to leave you with a really fascinating final thought to ponder. We've seen exactly how oxidation works today. We know that oxygen, the very gas we are breathing in right now, the gas that gives us life, is also the exact same element that causes strong steel to crumble into dust and fresh food to spoil and rot. So, what is this powerful, highly reactive element slowly doing to our own cells over a lifetime? Chemistry surrounds us every single day, and understanding it is the key to understanding our entire world. Thank you so much for joining me in this explainer. Keep exploring, and I'll see you next time.